All right, well, I'll start us off with a land acknowledgement. We wish to acknowledge this land on which the Fields Institute operates. For thousands of years, it's been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting is still the home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. And our speaker today is Jacques Bélair from the University of Montréal, and he's going to tell us about Fangcang shelters. So I'll give it to you, Jacques.
Thank you. So let me try to share my screen. Okay. So thank you very much for this opportunity to present some of the work I was involved in the last few years. So in fact, as most of you now know, the troubles began at the end of December in 2019, where Google monitoring enterprises like Blue Dot noticed that there was an undiagnosed respiratory syndrome in China. And in fact, in January of 2020, so 10 days later, at the one of the main university hospitals in Montreal, there was a warning that a new respiratory virus was coming from China. And of course, now we know that this respiratory virus is SARS-CoV-2. So as a light introduction, let me present to you a different perspective on SARS-CoV-2 and COVID-19. One of the issues that came out in managing the pandemic was how to deal with this new set of circumstances. And there was lots of discussions about what works and what does not work. And so at different points, especially in the spring of 2020, people were looking, so this is from a well-known periodical in France. So people were trying to determine what works elsewhere. So Germany, Denmark, Israel, and Vietnam. And then afterwards, this is spring of 2021, with the notion of introducing the vaccine, the assessment of the situation led this famous British periodical to ask what has gone wrong. In fact, one of the issues during the pandemic, especially the lockdown, was to deal with the breakup of social contacts. So different people with different walks of life took different perspectives on this issue. And psychologists tried to assess what was useful in keeping one busy during the pandemic and the lockdown. And so in 2021 was published the results of a survey of people looking at horror movies during the pandemics. So their conclusion was that looking at these movies induce higher resilience after the pandemic, and they had data. So this is a serious study since they have data. And so the main result, as illustrated here, was that preparedness for the pandemic as a function of the number of films seen was actually an increasing function. So this is a strange way of representing things, since the horizontal axis is actually increasing going right word. So seeing many is on the left, never seeing many is on the right. And so you see in this representation a decreasing function of preparedness as a function of the inverse of the number of pandemic films seen. So it's better to look at many movies. So unbeknownst these results, I had already implemented this algorithm. And in fact, I presented almost 2 years ago now an approach of looking at pandemic movies from a mathematical perspective. And in a Canadian context, an interesting example is one movie which is called Pontypool, named after a town in Ontario. And in this case, the means of transmission of the infection is language, and in particular, the English language. So in this case, the infected are not zombies like in many of the horror movies, but rather conversationalists. And as they say in the movie, that the first stage is you repeat a word, you get stuck, and then your language becomes scrambled. And then the third stage, you're distraught, and your condition is such that the only way that you feel as an infected person is to try and chew your way through the mouth of another person. So as is illustrated here, this can be summarized as shut up or die. And as is illustrated on the poster for the movie, this is a very Cronenbergian approach, named after the famous Canadian filmmaker David Cronenberg, who has had his share of horror movies of different types and conditions. Another interesting example in, I think, a Canadian context also is this movie from the 1990s, Black Death, which is a representation of the Black Death in the Middle Ages. And one of the issues in this movie is a group of warriors is trying to identify the source of the protection of one particular isolated village. And so they go there and try to determine why there's little infection in one specific village. And it turns out that there are some issues. Where does the infection comes from? This being in England, they say it comes from France, where all foul things emerge. And it turns out that as they specifically specifically say at the end of the movie, that this village and the inhabitants were not protected by a witch, because this is one of the issues, that they were simply remote. And so they're behind quite a significant marsh. And so when the marsh is crossed, and in fact, some of the investigators are bringing the infection with them. And so it turns out that isolation is what was protecting them. So the handling and management of the pandemic was, as the Quebec popular magazine Quebec Science illustrated in its May 2020 issue, that this was really a race against the clock, that medical doctors, virologists, epidemiologists, and mathematicians were fighting day and night against the pandemic. And this was labeled by the investigator as the hour of glory of modeling. And in fact, they interviewed some of the mathematicians involved, and of course they represented flattening the curve intervention and strategy to control the pandemic. So one of the issues that came out very quickly was the availability of different resources, masks at one point, and protective equipment for healthcare workers. So, and more broadly, hospital capacity and public health resources, in particular, hospital capacity is what I would be talking about in more details. And so this is not a new problem. This had been looked at from a different perspective in a different environment, in fact, for a different disease. A few years ago, by collaborators and myself, and in the context of looking at the control of dengue, which is a mosquito-borne disease, with limited public health resources. So one of the issues with many vector-borne diseases is that they're quite prevalent in areas of the world where public health capacities are limited and sometimes quite scarce. So the capacity to deal with the infectious is significant. And so one must incorporate the management with limited resources. And so what we looked at in this work was a compartmental model of the flavor that I'll be talking about later on, so I'll give more details then. So SIR in a more detailed representation. So one model and sort of process or transition for the humans, and another one for mosquitoes. So one of the issues with the access of resources and capacity to treat infectious is what is labeled the symbol mu in this case. So the second equation on the left, the rate of change of the infected is actually the recovery from the term mu. And this mu depends on the number of infected and on the hospital capacity, represented here as a number of beds. So basically, what we have is a decreasing function of hospital capacity as a function of infectious. So this introduces the idea that recovery from infection is slower if capacity is limited. So what is one of the consequences of this is that you can induce, so there are quite a few parameters in this model here. And so depending on the values of many of the parameters, so the betas, the Ds, the M, the R, the alpha, there's some situation where the fact that this capacity is decreasing as a function of the number of infectious means that you can have oscillations in the number of infected. So here the infected are represented in blue, and so depending on the parameter values in the model, you can get an oscillating number of infectious, which is problematic in terms of public health approach. If you try to control and you do not realize that oscillations are possible, then you may be too confident when the number of infections is going down, or too worry when the number of infections is going up. So understanding the dynamics in the model may help manage it and try to incorporate many of the conditions that you introduce by your approaches to managing. So at the beginning of the pandemic, the problem was not to get dynamics of an oscillatory nature or interesting dynamics. It was to bring the number of infections under control in terms of growth rate or in terms of sheer numbers. And so one of the techniques that were introduced was this use of the Fangcang Shelter Hospital. And in April of 2020, this was presented as a novel concept for responding to public health emergencies. And in fact, this concept came with a construction and operation manual specifically designed those Fangcang hospitals for COVID-19. And in fact, what I'll be presenting today is a work that was published by many members of this community in the Bulletin of the World Health Organization. And at the end of 2020, and this work was done, in fact, during the spring and summer of 2020. So what we were trying to do is understand some of the consequences on the control of the pandemic of the very quick construction of hospital care capacity that happened in Wuhan in February of 2020. So you may remember this media coverage of this very quick, very targeted construction operation where hospitals were built within days or weeks. And this was very, very intensive. And the object was to increase hospital capacity. And this is what these Fangcang shelter hospitals were. So this is the interior of these facilities. So you can see that they're not entirely sophisticated, but very high. They have a very high capacity. And of course, the notion was trying to understand and limit the number of cases that were being detected in Wuhan. And so one can, and this is how I will describe the model and the dynamics and properties of the model and the consequences of these constructions. If one looks historically, retrospectively, as the number of cases in hospital bed, and also, so this is the left vertical axis, number of cases in hospital bed, and the graph one must look at is the total cases, which is the triangle, and the rightmost vertical axis is the number of cases in healthcare personnel. So one of the issues in managing is the infection of healthcare personnel, because as I mentioned, the healthcare capacity, one is characterized, as I mentioned, by protective material, and also hospital bed, but also hospital bed that are manned by healthcare personnel. So one of the issues is to try to have a notion of and control the number of infection of the healthcare personnel. So here, in this graph, composed graph of 3 graphs, we have a the number of confirmed cases in hospital bed, the confirmed cases in healthcare personnel. So the healthcare personnel is is the dots. The new cases are the stars, and the triangles are the beds in the Fangcang Shelter Hospital. So one can see the effect of introducing these hospitals. So from, this is illustrated February 5th to 22. And the healthcare personnel from January 23rd to February 11 was going down to confirm cases. And one can see the effect of the total new cases, the stars, that went significantly down, especially comparing February 12th when they were introduced to the following. So I'll come back to more detail representation and look at data, historical data further on. So what we'll be looking at is construct a compartmental model of SEIR nature. And we will distinguish between susceptibles who are not healthcare personnel and susceptible who are healthcare personnel. So given the role played by the healthcare personnel in determining the healthcare capacity, we will actually be looking at two different parallel streams of SEIR models, one for the non-healthcare personnel and one for the healthcare personnel. So W is non-healthcare and H, so the W for who are not healthcare. So SEA. So one of the issues that came out relatively early in the pandemic was the existence of asymptotic infected, as this was an unusual set of circumstances. Even the acceptance of the existence of asymptotic infected was not entirely obvious at the beginning, because I remember having specialists, virologists, epidemiologists interviewed in the media, and they were quite skeptical about the first reports of asymptomatic cases, but it turned out to play a significant role in the pandemic. So we will look at these. One can summarize as a coupled, it's like two coupled models, one for the non-healthcare personnel, not healthcare personnel, and healthcare personnel. So we have the usual SEIR. So we add the asymptomatic AW in both the non-healthcare personnel at the left and the healthcare personnel on the right. So the personnel, the healthcare personnel is the healthcare personnel in the hospitals. So the designated hospitals, or that are now called the Fangcang hospitals. So we're looking at the personnel from, as usual, SEIAR, and we differentiate or isolate between untreated and treated people. So W1 will be the untreated, and W2 will be the treated who will recover and will eventually become recovered. So in terms of equation, we have the model equation for the non-healthcare personnel and the model equations for the healthcare personnel. So these equations correspond to the process that is illustrated here, and eventually everyone ends up recovered. So this I call phase 1, because in phase 2, I will introduce these observation awards. So a new set of hospitals, the ones that are constructed. So the designated hospitals were the regular hospitals. The observation awards are the new hospitals. So there's a new class or a new set of individuals now that will be introduced. And these are the susceptible healthcare personnel in the shelter hospital, in the Fangcang shelter hospital, the exposed, asymptomatic, infected, and recovered. And so these are the ones that are now at the bottom. And so the relationship between them is that the patients admitted to the designated or regular hospitals are the ones who were had to be treated previously as before, but now there are some who are also transferred to the Fangcang Hospital, the observation wards, and some of them eventually will make it to the regular hospitals. So with and without the Fangcang shelter hospitals is the addition of this third or this second set of healthcare facilities. So in what I call phase 2, the addition of the Fangcang Hospital will introduce, in addition to the 2 sets of equation for the non-healthcare personnel and the healthcare personnel in the designated hospital, there will be an additional now set of modeling equations for the healthcare personnel in the observation ward or the Fangcang Hospital. And one can see that the model structure is the same. And so in phase 3, what happened was the healthcare personnel were identified. And so comparing the bottom graph, the bottom diagram on this representation in what I call phase 3 with what I call phase 2, is that now there are no longer this introduction of the susceptible inside the hospital themselves. So the entrance to, so the inflow to the designated hospitals is completely through the observation wards. And so comparing the treatment of patients when there are observation wards of Fangcang Hospital and designated hospitals, one can see that only the transition through observation wards unless there's an infection will be, so only people with symptoms will be admitted to designated hospitals. So the model equation for the non-healthcare personnel in this third phase will be changed slightly. So what we'd like to do is look at the different behavior possible in the 3 phases, especially in the third phase, which is the one where the full deployment of the Fangcang Hospital was realized. So we can look at these model using the usual analysis techniques. So try to find disease-free equilibrium, measure a basic reproduction number. And so In this case, of course, as usual, the disease-free equilibrium will always have non-zero entries, which are susceptible and recovered. And the basic reproduction number is, as is common in these type of models, will be a maximum of 3 sub-reproduction number in each of the subpopulations, and these can be completely determined from parameters which appear in the modeling equation. And so for these models, we can introduce a time dependence on the reproduction number, because as is well known, the basic reproduction number strictly only applies for a totally susceptible population. So what we did is introduce what we call an instantaneous risk index, which is this max of the 3 quantities are OW, R0W, R0H, R0G. So W and H, I remind you, refer to the non-healthcare personnel, and G is the healthcare personnel in the Fangcang hospital. And so we look at a slight variation of each of the R0s, which introduces an element of instantaneous dynamics in the pandemic. So these are the additional terms. And so if we now look at some simulations from the model and compare it with data, so actual data for the numbers of infection in Yuan from January to March. So the stars are the number of cases, and the line is the data fitted to these lines in question, the fitted data. So you may remember that on February 12th was a big change in the criterion for diagnosis. So that's why the number of infection made this huge jump. And so the number of deaths now is well represented by the model. And here's the, I think, most striking graph, which is the number of confirmed cases according to the model under different hypothetical scenarios from January to August. And on the top is a look at the number of daily confirmed cases with different opening dates. And the bottom is the number of beds used. So the changing the different opening dates at the top, one can see a comparison between what's labeled February 5th, which is the gray or dark line. So the actual data that is from what really happened, that the hospitals opened on February 5th. And one can compare what would have happened had the same hospital been open on January 23rd, which is the dark green line, or January 30th, which is the mid green, or February 2nd, which is the light green line. So one can see those 3 curves aligning one on top of the other, confirming or compatible with the notion that the earlier opening of the shelter hospitals would have prevented the number of confirmed cases by the use of isolation. And what is most striking on this graph is that if the opening had been delayed by a single day, which is the dotted, which is represented by the dotted black line, then the number of cases would have increased essentially tenfold or close by. And one in looking at these graphs should keep in mind that the black dotted line has is a different vertical scale on the axis. So the 2 to 6 million confirmed cases only apply to the dashed black line. So this is an illustration of the importance of timeliness in deploying the intervention capacity. And at the bottom is the number of beds used with different scenarios similar to the one above. That the earlier, the more beds are available, then the less cases will occur. So the model corresponding to reality is the green line at the bottom, the green, the dark green line. So if the capacity is increased as the line is lighter, or decreased for the black line, the black dashed line, then we get a similar behavior in the number of cases. So opening the hospitals at the top and having a significant capacity at the bottom does show its usefulness in reducing the number of cases. And here we compare the transmission rate in the absence of hospital and the number of beds used, and comparing here the dashed green at the top is the model, and transmission rate is reduced by different factors. And we showed consequences and the number of beds used. Also in the hospital, we see the number of confirmed cases in a representation similar to the one that was shown before. And we can also look at the cumulative number of cases. And transmission rate in absence, which would be a terrible scenario with the number of deaths in the millions. So, and we also get the number of transients in the different configurations from the start to the use of these hospital beds. So in trying to look mathematically at these dynamics, we looked more recently at the delayed model, so a simplified model for the transmission and control in these hospitals. And so in this case, what we looked at was more of the dynamics in between compartments, but at this reduced number of compartments. So once again, an SEAI-HR model. So this is an SIR model with an exposed class and a symptomatic class, a division in an infected, and given our emphasis on the hospital capacity and compartment with hospitalized individuals. So we looked at the two scenarios with and without the Fangcang hospitals. So the one at the top is without, and the one at the bottom has these hospitals. So of course, what happens is the hospital, as was the case before, is divided between the blue H compartment, which is people hospitalized in regular hospitals, and the green F hospital compartment is people who are hospitalized in those Fangcang hospital. And so if at the infectious stage, there's a division between people who will be led to one or two of the classes of the hospitals. So in this case, we were interested in looking at the role of waiting time and combination of waiting time and the number of available beds. So we explicitly put in the equation the role of waiting time before admission in either the Fangcang Hospital, which we label Tau 3, and the designated or regular hospital, which we call Tau 2, Tau 4, Tau sub 4. So in this case, the infected in the compartment I2, which are the late stage of the compartments, we can write them as basically the sum of people who were infected and have not recovered and are still infected and may or may not be admitted to hospital. So this is this set of equations for this SEAIHR model. So that's without the Fangcang Hospital. And so if we put the Fangcang Hospital in, then we get the second set. So these two infected compartments IM and IS in the presence of the Fangcang Hospital then have their own equations. And we end up with this SEAIIFHR model with explicit representation of the Tau 3 and Tau 4, which was the waiting time to get admitted to the respective hospital. So we manage, as a first step, to do some mathematical analysis of a simplified model. So we assumed that the delays would be constant, and we first looked at the absence, in the absence of the Fangcang Hospital. So we also looked at constant delays in the presence of the Fangcang Hospital. So we were able to do some analysis, which was more complete in the case of the Fangcang Hospital. So we have the respective disease-free equilibrium with and without the Fangcang hospitals. You can see more compartments in the Fangcang Hospital. And this, given these disease-free equilibria, we can compute the basic reproduction number by a next generation method. So basically, using the VF partition that is common in the most standard approach of the computation of R0 with next generation matrices, we can divide the V component in 3 and get the R0, as is well known, as a explicit representation of the spectral radius of minus the product of the matrices F and inverse of V. So we can do that explicitly, explicitly in this case, and have a complete representation as the different parameters. And we also can establish the existence of an endemic equilibrium, which will exist, as is most often the case when the R0 in the case of the Fangcang hospitals is greater than 1, and we can also in this case establish the global stability of the disease-free equilibrium when R0 is less than 1. And this endemic equilibrium, which exists when R0 is bigger than 1, we can look at and try to establish its stability, and the presence of the time delays that were mentioned in the title of this talk will lead to a characteristic equation, which is not entirely pleasant. In fact, the equation is the one that is the product of A and B. Given that the matrix is a block matrix, we have to multiply the equation at the top with the equation in the middle. So this sixth order equation with two exponential terms. All of the coefficients Aij being different combinations of the coordinates of the endemic equilibrium or some of the dynamic parameters from the equation. And we can establish a sufficient condition for symplectic stability of this equilibrium by analyzing this characteristic equation. We can have an estimation of these different parameters from the literature and some estimation. And we can compare simulations from the model with actual data fitted in U1. For the number of deaths, cases, the beds in the Fangcang hospital. So at the lower left, we see the real data with the fitting of the model using these different parameters. And the impact of the Fangcang hospital becomes clear when we compare the number of cases confirmed and the number of deaths as a function of time with and without those hospitals. Without is the blue line, with is the red line, and the vertical axis is times 10 to the 4 or 5. And we can look at the influence of these two time delays, the waiting time and the regular observation ward and the Fangcang hospital, and also have a idea of the elasticity of this R0 to determine which of the two waiting time for the two classes of hospital is the most significant and affecting the value of R0. And so this is what's represented here, the tau2 being the recovery, the regular hospitals, and tau4, the Fangcang hospital. And the specificity index is a ratio, a weighted ratio of these two numbers. And reality is the red line in this heat graph. So this is a short perspective of the work that has now been published in the Bulletin of WHO, as I mentioned, in 2020, and more recently in the Science Journal of Applied Math. So as one might have guessed at this point, the more mathematical aspect in the Science Journal of Applied Math, February of 2023. And in trying to determine the level of details in a model and how should a model represent reality, I am inspired by this text of the Argentinian writer, Jorge Luis Borges, who's also had written on the library, Infinite Library. And so in this case, what is relevant is this notion that the art of cartography, so here one should think of cartography as modeling, So the art of cartography was such perfected that the map of a province was in one-to-one correspondence with the province. So the cartographers struck a map of the empire whose size was that of the empire and which coincided point for point with it. And it turns out that this was not entirely satisfactory. And so in all the land, there is no other relic of the disciplines of geography, but tattered ruins of that map inhabited by animals and beggars. So this is a warning on models which are too close to reality. And I will end here. Thank you very much for your attention.